In this video, we are going to look at the kinetic molecular theory of gases. It's 5 postulates, and we're going to look at some exceptions to these postulates and some application of these postulates. So let's get to it. The very first one here is that the volume of a gas is negligible compared to the volume of the container. That is to say that gases are mainly empty space. Next point. Gases move in rapid, straight-line motion between collisions with one another and with the walls of their container. There is no loss of kinetic energy when two gas particles collide. If they did lose energy, then they would probably start to gather on the floor, and we know that gas particles don't gather on the floor. They continue to fly around. The next one, in the gas phase, there are no attractive forces between particles, and this differs from liquids and solids that have attractive forces for each other. These gases don't have attractive forces. If they do, they would probably attract each other into giant clumps, and we would find giant clumps of gases on the ground, which again, we do not. And in our fifth one here, at any given temperature, the average KE is kinetic energy of particles in the gases are the same. So they all have the same energy. How is that possible? Well, we'll investigate that in a little bit. We do have to know that if a gas obeys all of these statements, it's called an ideal gas. And most of the time, 99.9999% of the time, gases obey all 5 of these postulates, so they're known as ideal gases. But there are a couple of scenarios where a gas deviates from these 5. So a real gas is a gas that deviates from the behavior of an ideal gas. And real gases occur under 2 conditions, and they're kind of rare conditions as well. The first one is under high pressure, and the second one is under very extremely low temperatures. I'm going to elaborate on these 2 points on the next slide here. So real gases will experience forces of attraction under high pressure, so that's the 4th postulate that gets violated. And secondly, they will also become a significant portion of the total volume at low temperatures. So that would be our second point, and that is of course violating the 1st postulate that says gases are mainly empty space. So what we can do is we can actually sort of do an application of these kinetic molecular theory postulates and something that is called Graham's law of effusion and diffusion. Now, effusion and diffusion are kind of essentially the same thing. They are, if you open up a container of gases, those particles inside the container are going to start to move around the room, and that's essentially what effusion and diffusion are. Okay, so it's just particles escaping. So we talked about the 5th postulate that said at any given temperature, the average kinetic energy of particles in all gases are the same. Well, hang on a second. All gases are not the same. They're different sizes, they're different shapes, they definitely have different masses. So how could this be possible? How could they all have the same energy? Well, we can investigate this a little bit here, and using an equation from physics, we can actually prove this is possible. So here's what we're going to do. We're going to calculate the velocity of helium and argon gases if they each have the same kinetic energy of 100 joules. Now, the formula we're going to use here to calculate this is kinetic energy is equal to 1/2 mass volume squared. So we're going to do it for these 2 gases. The only thing we need to know is we need to know the molar masses of these gases. So helium, if you look it up, is about 4 grams per mole. And argon here is about 40 grams per mole. It's about 10 times bigger. So if we just do a little thought experiment, and let's break this in half. Here, the screen, we'll do this for helium. So I'm going to write my formula down. And I'm going to plug that 100 in for the kinetic energy. I'm going to keep the half. And the mass would be 4. And then we have v squared. So we can simplify this a little bit. Half of 4 is 2, 2v squared. So we'll divide both sides by 2, we get 50. And then we want to do the square root here of each side. And it should work out to a little more than 7. Let's just put 7.1 meters per second. So that's how fast helium atom would be moving. Okay, let's compare that to argon. So argon, again, same formula, kinetic energy 1/2 mv squared. We'll put the 100 in there. We'll keep the half. Our mass this time is 40, and that's v squared. So this is going to simplify to 120 v squared. Divide both sides by 20, you get 5. Take the square root of each side, and we get at about 2.2 meters per second. And we have made a discovery here. We have discovered that if gases have the same energy, then they have totally different speeds. They're moving at different velocities, I should say. And that is directly related to their mass. So helium was very light. It was 4 grams per mole. Argon was twice as much at 40 grams per mole. And so the conclusion we can draw here is that the heavier the gas, the slower it moves. And the lighter the gas, the faster it moves. And that is essentially what Graham's law is. So, the heavier a gas is by mass, the slower it must be moving, and vice versa. So we can do a little example problem here using Graham's law. So which gas will effuse faster? All we need to do is know the molar masses of these gases. So neon is 28 grams per mole. Argon is 40 grams per mole. So which one's moving faster? It would be the lighter one. So therefore N2 is effusing faster because it is lighter. And we can even try this again, this time with bromine gas and water vapor. So bromine is, well, it's about 158 grams per mole. Water vapor is a little more than 18 grams per mole. But water vapor is clearly lighter, but this question is actually saying which one's going to move slower. So we're looking for the heavier gas here. So therefore Br2 will diffuse slower because it is heavier. And that, children, is Graham's law in action.
I promise to show you something really cool as long as you promise not to try it at home, okay? Okay. Now, everyone wants to know why my voice sounds higher when I inhale helium.
The simple fact is that helium is 6 times less dense than air, which means sound waves travel through it much faster, which makes my voice sound much higher. Now, the same effect can be achieved in reverse if I inhale something like
sulfur hexafluoride, which is 6 times denser than air. I inhale some of that, and my voice gets really low, although somehow I'm still